First of all, thank you all for coming. Today's lecture is going to be on Bayesian optimization for material discovery. And this is a topic I've recently started working on, and this is as part of this fellowship. And my background is on, as I did my PhD in physics, and I was really looking in depth at specific material or like device type and trying to understand how they work and what are their limitations. And now I moved into material discovery because I can see that there is a lot of potential in using the knowledge I've gained through like an in-depth study or like an in-depth kind of study of certain material to explore the chemical space or the material space and find new material for specific application. So for this lecture, I'm going to go through it in 3 different points. So the first point is just trying to make sure that we all understand what is material discovery, what I mean by it, and how we could use AI or data-driven approaches to accelerate it. The next point is like an introduction to Bayesian optimization. So sorry again for anyone who's already an expert on the subject. This is me trying to learn about it, and I'm going to present it in that way, trying to present it as if I was on the room 6 months ago. I'm trying to share with you what I've understood so far on using this method and how it applies to material discovery. And finally, I'm going to go through like some applications from the literature and an application that is closer to my own research, and we can discuss that in a lot more detail. So to make this talk a little bit interactive, I'm going to use this tool called Menti. So if you can all go into menti.com, use any of your devices, go to menti.com and use that code so that you can access this room and just answer the first question if you manage to get access, so that we establish that we're all able to use this. And then throughout the talk, there's going to be like a slide like that popping up, showing you, asking you a certain question, and then you can answer, and then we can discuss based on your answers what what that means and how you feel about it. Because there's a lot in it. So we've got 7 people so far out of 8. Oh yeah, you yes. So we're missing 1 person. Or also sorry, didn't get your name. Whoever is online. I don't know if you managed to get it as well. 9.
Yeah, it's all good.
Perfect. Okay, so we're all good. I'm just going to go back to the slides now. So first of all, what do we mean by material discovery? A definition that I found is material discovery refers to the process of identifying and developing new materials with specific properties. So you're looking for, in the material space, you're looking for a specific application. Let's say, for example, looking for material for photovoltaic application, something that absorbs light within a certain color and produces electricity up to a certain efficiency, or has some other properties, like it can be flexible, or it can be transparent and things like that. And then, or also think about the weight and other things. So there's a lot of properties that goes into it, and you're looking for materials that have that kind of properties or characteristics. Funny thing, I've asked someone yesterday about what do you mean by material discovery, and the first answer they gave me was finding some materials in nature. So mining a new material. It's something that might have been useful a few hundred years ago, but nowadays most of the materials are found through new synthesis and by putting together new, trying different approaches, or isolating new materials from one another. And it's not as easy as stumbling across a new thing. But that's kind of my understanding of material discovery. And how does it work? So how do we discover materials? So when I Googled it, the first thing that came out is all of these interesting stories about how some materials have been discovered. For example, penicillin, it was discovered as Alexander Fleming, after doing his, he was working in his lab trying to see find a way to fight a certain bacteria. And then after a week, he left his lab for a week, and then he came back, found in the trash that there was mold around the bacteria that was stopping it from growing and also killing it. So he discovered penicillin just by chance, just by looking into his trash, and he found that, oh, by the way, this mold seems to have the right properties that I'm looking for. And there's a lot of other stories. We can also look into graphene that was discovered recently. So they isolated the graphene like this thin sheet of one atom layer of material by just looking into the tape they were using to clean the graphite. So it's just by luck they managed to find it. But this is these are the most famous stories that you will hear. It's quite common, but yeah, there is also behind it a lot of other approaches that is like a bit more scientific, where you do a lot of trial and error. So even, for example, in the story of the penicillin, once they've actually observed that there was this mold around the bacteria and that was stopping it, how they managed to isolate the penicillin, or like kind of synthesize penicillin out of that, it took them years and years of trial and error. So it's not as easy as just stumbling across in it. So sometimes like breakthroughs are done by luck, but there's a lot of trial and error that comes afterward, which is like a scientific approach. Here I'm also showing an example of Thomas Edison on how he found the right material for his bulb. So he was the first one to patent a light bulb, and to find the right material for the filament, he tried more than 6,000 different carbon-based material, and he looked into, like, he asked all people around him, like anyone who's that he knew about the relevant material, how he could isolate them, tried different nature-based material, and then each time after an experimentation, he tests it and tries again and again and again. And even if it doesn't work, he just keeps on going. And then at the end, he managed to get something. And this is where, like, if we were to use this approach, we would also we can improve that by using nowadays like computational methods. So computation method can help you, would help with like assessing how, like by developing the right models, you don't have to do as much trial and error. You can assess the potential of a certain material by modeling it and seeing how good it would perform in real life. You also can use computation method for knowledge generation and establishing your hypothesis and trying again and again. So this is one way, like this is starting from the 1950s. We've started like actually incorporating modeling methods a lot into our approach, and it has accelerated the material discovery by several folds. It's very unclear how you can actually assess that, but it's something that we can discuss in a second. And now since 2000, with the development of, with data-driven approach and AI, we can even further accelerate this by using like generative model to generate new molecules or new material, and accelerate the discovery through also optimization and making sure that we do we kind of reduce the number of trial and errors and just use all the knowledge we built up so far to guide our search of the material space. So the first question I've got for you here is really on the so what's the potential of a certain material discovery approach, and how was it useful nowadays? And we can also discuss on this a bit more. So you've got a scale on your phone, if you manage to see it, showing you like how you can score each one of them based on these two questions.
So the first one is potential.
Yeah.
And the second one
is actually how much it helped you discover new material. How many, like, for example, according to you, how many new materials have been discovered through each one of these approaches? Yes.
Here the y-axis is how much it's been used, I guess, and the x-axis is potential.
Yeah.
So I mean, it seems like AI and data-driven approaches have a lot of potential but are not being used a lot currently, and trial and error has average potential but is being used a lot. And then something like luck maybe has not a lot of potential and seems like it's not being used a lot.
So I think from my experience, I would say that's kind of how it's been going on for the past, been in a specific field like organic photovoltaics for the past 8 years, and that's more or less how it is. So the computational material design and AI have got the most potential, but they're not as efficient. Whereas, so far, the new materials that are the most efficient have been mainly found by trial and error, as I would even say luck sometimes. But it's more like trying different materials. Someone tries a new material that has been used for another application, and just by chance it worked. Even modeling and computational approaches are not really the ones driving the field so far, and that's one issue that we could potentially try and that AI and data-driven approaches might address by making the computational methods a little bit more accessible, or slightly more increase their predictive power to a certain extent.
How about the stability of the material? So, in terms of these different methods, let's say that some of these methods will very easily find very novel and promising materials, but they're not stable. So let's say they break down very easily under irradiation, for example.
Yeah, so stability could be one of the criteria for your material discovery approach. And sometimes, some of the materials that you find are more stable, are less stable, but they're very efficient, or they're also dangerous for they might be, how do you say it, harmful for the environment, but they are still very efficient. But those could have some, so it depends on your kind of material discovery approach or the initial question that you ask. But sometimes it's interesting to see that even some people would focus on efficiency first and then think about the other implication, like the stability and the toxicity as a next step. And one example I would say is perovskite. That's a material that has been heavily used now that has been used a lot in photovoltaic applications. It started with something that was heavily toxic based on lead, and nowadays there's a lot of research on it, and they've managed to make some similar material, similar structures that are less toxic and also more stable. So that's, it's definitely a very fair question, but it also depends on what...
Has that development been driven by then trial and error, or iterative, let's say, engineering?
So if I were, for that example in particular, the discovery of perovskite was mainly luck to a certain extent, I would say. It started with people working with a different type of material, like dye-synthesized solar cells, and then and those were mainly solvent-based. They were very they were different from the ones that are used nowadays. And then they just tried a dried version of it, and it managed to get very high efficiency. So it's both. It started with luck, where they just looked into it and they found that, this material is interesting. But then they used, going from the initial discovery that gave them, this material works, and a material that is actually higher in efficiency. It went through a lot of trial and error and using a lot of the background knowledge. So it's very, so that's why it's very hard to say whether luck is really that bad. Because at the end, the initial material, the breakthrough, often happens by luck.
I have a question. Is there I guess, could you use AI and data-driven approaches to essentially engineer your own luck, if that has if that means anything? Because I feel with these approaches, you can go through many more different permutations, right? So is there is there an optimal way to actually work luck into I guess more organized fashion, so like more organized approaches?
So it's definitely a fair question, and it's so the idea is with AI and data-driven, you can try a lot more material, so you can screen very fast, and hence you have higher probability of finding something new. But it doesn't really work that way because sometimes, like there's the probability, like the material space is so big that even if you increase the number of trials that you do, it doesn't change, like even from a probabilistic point of view, it changes it by a slight amount, and that's not enough to actually explain make the potential of AI a reality. But then there are ways where you can try and think about it in this way, and how can you incorporate luck into it, and how can you kind of increase the exploration aspect of your algorithm or your approach so that you're not limited by things that you've tried so far, so that you force your luck to a certain extent. But that's definitely a good thing to consider. And yeah, these are questions that kind of stays in your mind whenever you think about material discovery and AI and computational approaches. Okay, I'm just going to pop back to the slides and now go into the question of material discovery. Is it actually an optimization problem? So I'm taking this example again. Since I'm from the field of photovoltaics, I've mainly been giving you examples on that. Now again, so this, let's say for example, we want to make these very nice, colorful solar cells that absorb light in a specific color and produce energy as much as they can. So they need to absorb light in a specific region as well as being quite efficient at generating electricity. And to do that, you build your device as such with on top of your glass, you have some electrodes, you have your active material that's the one absorbing light or doing the photovoltaic effect, and then some other electrode, like the counter electrode on the other side, and then you have some transparent layer on the other side, like on the top, and then something to kind of isolate it from the environment. And basically, so if you want to look into just optimizing this active layer with some properties that would work within this kind of device structure, so you need to kind of look into the space of these type of molecules that you can see here. So potentially you're not very familiar, I don't expect you to be familiar with chemical structures or things like that. So these are just ways of representing your molecule with each node would be an atom of carbon, and then you have some other atoms that are different from carbon that would have a specific name, for example, here sulfur or something. And these, you can synthesize them, and there are quite a lot of them. And what we want to do is kind of maximize, find the right molecules that have a certain number of properties. And we want to look into this very big space. So we could think about it as, if we know the space of all the molecules that we can make, can we just try and maximize a certain function that we've defined previously and then find that. The problem is here, we've got, just by looking at this type of molecule, from this number that is insanely big of possible molecules that you can actually look into. So you need some kind of smart way of looking into that space, but also you need to define your search space properly, limit it, and incorporate a lot of background knowledge in your search approach. Hence, when I was looking into this question, found that, you can either have some kind of heuristic approach where you just do some evolutionary algorithm and look into this space and search as much as you can and evaluate with a certain metric. That can be the evaluation can be either computational approach where you calculate the properties within 5 minutes or days, or the evaluation could be experimental. You actually go and synthesize those molecules, try them, and then make them, and that way your evaluation would take days. So if we were to do any approach, if we just do a heuristic approach or random search or an evolution algorithm, it might be quite demanding, and it's very hard to incorporate any knowledge we had so far. But we could use machine learning to help with the screening and predict the performance of that material very quickly. The problem is if you do that, well, one thing is you cannot run it on all of them, and also you don't actually know how much your, like the error of your prediction, because you could train your machine learning on subspace that has been already calculated or that has been already measured, but that's quite limited and there's no way to know your error. Hence, you need to kind of think about a smarter way, and that's where I stumbled across this Bayesian optimization, which is a nice, like a way to kind of incorporate your background knowledge and also have variance into it. I'm just gonna ask you a quick question here about like how much do you actually know about Bayesian optimization, and depending on that, we can. I'm gonna tailor the rest of the talk. So. Okay, we've got an expert on Bayesian optimization.
I have a sort of side question.
Yes.
These window-like transparent solar panels,
Yeah.
they exist?
Yes.
Right? Okay. And so what is hindering them being used a lot more than they are? Like cost, I guess? Or
There is cost. There is it's cost, efficiency, and yeah.
so by efficiency you mean like they don't produce as much energy as standard solar panels, or
Well, it's like you can think about it as how much it costs to actually produce them or like incorporate them into Windows and how much energy you get out. And if your return is very low, then it's very hard to convince people to actually use them. So yeah, that's one thing. And also, there's the question of stability. They might not be as stable as you want them to be, especially if you're going to use them in like buildings. They would like you want something that is stable for like at least 10 or 20 years, and these tend to be slightly less good.
So, in the context of that light change color to electricity thing, you
Yeah.
have the formulation of max f of x.
Yeah.
X is in space, right? So,
Yeah.
the f is a function of how much electricity a small area would produce, and your x is the space of colors. I'm trying to map the problem to the way you
So X would be the space of potential molecules.
molecules.
So yeah, let's say you can make your molecule by putting like there's certain rules of how you can make your molecules, and that if you just look at molecules within a certain size, like number of atoms, then you have quite a big number of molecules that you can screen through them. So yeah, the idea here is your space is the space of molecules, for example, or space of materials, and your f, like the function that you're trying to optimize, is you can think about it as the power conversion efficiency they get at a specific color, or you can also kind of have it with the power conversion efficiency plus the transparency or like the visual aspect of it. So the function is up to you, but these are examples. Okay, so we've got everyone here. So most of you, well, we've got a mixed bag. So we've got like people who are experts, people who mainly heard about it, and people who had a course but don't know much, like haven't actually used it. So hence, in the talk, I'm going to go, like in this lecture, I'm going to go through it. I go slightly through the basics, and we can start from there. But I think it's still, even if you're an expert, it's still interesting to think about what are the limitations and how you start, like how you define your problem from the very beginning, and what would those, like how the way you kind of define your algorithm or like write it down affects how you can use it in real life. So going back, so here the Bayesian optimization, what it is, it's kind of an optimization approach where you would use Gaussian processes, and so each so you use like a Gaussian process to give you the possible functions that would that would fit the initial points that you have, and then so that's what you use. So you start like with the initial data set that gives you like x and f of x. You fit your surrogate function here. I'm mainly going to be talking about Gaussian processes as the surrogate function because they give you both the mean and the variance of in each point, and then you would optimize this acquisition like the acquisition function. So basically, for choosing the next point, you would choose it considering a certain number of criteria, and these criteria would be through like optimizing this acquisition function. And here in this kind of, I took this from Wikipedia, and they are showing like 3 different acquisition functions on how you can choose the next point to find the maximum. And basically here, the idea of using Bayesian optimization is really to have the least number of trials or like evaluation of a black box function that is hard to compute to find the maxima as fast as you can. And in a one-dimensional case, it looks like this. It's quite nice, and normally it should work, and it can fit almost any functions. It's not like it doesn't rely on you having a gradient or anything. So it's not going to be as efficient as any optimization approach where you actually can compute the gradient, or but sometimes you can also kind of incorporate it. But it's quite useful when you have such a big problem like for the problem that we were talking about, like where you want to optimize this power conversion efficiency on materials. So it's very hard to define your function, or it's often not derivable. So you can use just like the Bayesian optimization and just consider your function as a black box. And you kind of change the approach from fitting your, like from trying to, like you kind of, instead of just optimizing your initial function, you try and approach your function with the surrogate model and try to optimize the your acquisition functions throughout. So,
sorry, can I ask, what were the, I cannot see the labels of the plots, so what are the plots actually?
So here, these are like 3 different acquisition functions. So we've got expected improvement, that's kind of how much improvement are we going to get based on the maximum we already have from the initial points. There's upper confidence bound, so it's just you take the mean of your prediction plus a certain variance and then take the maximum of that. So it's kind of taking the maximum of potentially just the outer, like the thing that on top, and then probability of improvement, which is slightly similar to expected improvement. But I'm going to go through those later on.
Comment. Is Bayesian optimization a global optimization?
So I would say it's a global optimization, but it depends on how you define your kind of acquisition function or your exploration and exploitation aspect of it. So ideally, you can use Bayesian optimization to really find the global minima or global maxima, but you can always fall in the trap of having getting stuck on a local minimum or maximum.
I guess you have some sort of smoothness assumption on the function, which might be implicit in trying to fit the Gaussian process.
Yes.
Okay, so it's in the fitting of the Gaussian process.
Yes, and we're gonna get to that in a second. So that's, I don't know if you must have come across like what a Gaussian process is and how it works. But basically, what is a Gaussian process? So this is me trying to understand what it is. So a Gaussian process is a probability distribution over possible functions that fit a set points. So here I'm just showing you like sample of different functions that you can have on this space. So like one-dimensional space from 0 to 1. What are all the possible functions that you have? And so a Gaussian, like basically, you can have any of these functions. For each point, you can like it has, you kind of sample it from a certain distribution, and you would use like here we're going to be using like Gaussian distributions overall to describe the point. So here the idea is if you have this type of functions, you can fit anything basically. The only question is how do you go from this to actually using it for a regression? And that's where, so if we think about it, this, like, if we don't have any points, so the possible, like, for each, like, all the functions that we have would be kind of distributed. If we consider that our functions are also follow like some kind of Gaussian distribution as well, then all the possible functions would be here with a mean around 0, and that's it. Here we defined it in that way, and then once we have any observations, that's going to start limiting the possible functions that we have, and the more points we get, the more we will get closer to the real function. And basically, yeah, so, and then doing this, or I kind of get into the kind of deriving the right way of defining your predicted mean and your variance at each point depends on the variance between your points, or like the covariance between the different points. And that's where, so here, the way we define our Gaussian process would use like multivariate variable Gaussians. So the probability of f of knowing x, knowing so we get that's going to be defined as like a normal, multivariable Gaussian, which is defined by its mean vector and covariance vector. So here, this is just an example of a multivariable Gaussian in 2 dimensions, and showing how things can change when you have, how your distributions change when you change the covariance between the 2 variables, x1 and x2. And when we're thinking about it in the case of the functions, or like Gaussian processes, so our variables would be the value of f of x1, so f of at position x 1, 2, 3, so you kind of define your space in a certain way, and that gives you like your, so yeah, the value, like the variable that we're looking at would be f of x1, and the mean would be the mean at point x1, and then our covariance matrix here defines the covariance between the different points x1 and x2, for example. Basically, if we increase the covariance, then our 2 variables would be highly correlated, and that kind of limits the distributions in a certain way. Then, if we think about it in the case of functions, so here I'm just showing an example where we increase just the covariance in a uniform way throughout all the points that we're plotting here. So we're starting with no correlation between the points, then we have every function is possible. We increase the covariance, then the point starts, like, so each point would be highly correlated with, like, each value of f of, for example, here, this x3 would be related to f of x2, and if they are two, like, the correlation is 1, then we get if we have a point at the beginning, then it will be the same for the whole function, and we just have like flat functions. Hence, it's quite important, and this is where like the definition of the covariance has strong impact on how your Gaussian process would work and how much it can fit different functions. And that's where this question of smoothness comes in. So if we go from this case to something that is a bit more useful, and we want to actually use it to fit, so we have like these points x, f of x, like these observations in red, and we want to predict the values of x star. So basically, what we're trying to predict is so what we have is that the distribution of f and f star, so f being like the values of f of x and f star being the values of f of x star, and they are defined as a function of their mean values and the covariance between these two, the two distribution, like the two variables. And we usually would just kind of use a mean of 0 to simplify things. And then what we actually want is to go from this distribution to a distribution of f star knowing the values of f of in x, and x star. So going from here to the other one, we go through some maths that I've put up here. I'm not going to go into too much detail about the theorem, but the idea is that you can define your this distribution as the normal distribution, with the mean being related to these different covariance, like the covariance matrix. So K star would be the covariance matrix between x and x star. K would be your covariance matrix of x, and then K star star would be the covariance matrix of x star and x star. And these would have different dimensions. And why the reason why I wanted to put this up here is that just to show you like the kind of computation complexity that is needed to actually derive this, is that you need to invert this matrix here, and that kind of gives you a complexity of n to the power of 3 that kind of limits how you can use this Gaussian processes. So it's highly limited by the number of points that you can consider in it. So the more observations you have, the harder it would be for you to actually compute the mean and covariance for the observations. Hence, that's one of the limitations that we need to keep in mind. And you cannot use, you can, but it just takes you much longer to actually calculate these values. So I've been talking a lot about covariance matrix, but in practice, what you need to define is a certain, you need to kind of define how you get that covariance. So it's something that is a function of, so it can be a function of how close your different points are in space. So for example, here we can use radial based kernel, or this is kind of a Gaussian based. And this tells you that any points that are close in space would have, the value of their function would be close as well. So that kind of smoothens out your space, and that kind of, so that makes your Gaussian process work more or less better depending on the function that you're looking at. So you can think about it as, you can also, these would have some hyperparameters that goes into them, and these hyperparameters kind of also define how strongly this the covariance would be if they are close in space. So if we just focus on the length scale here, L, so the higher the length scale, so here I'm just showing the same kind of Gauss, the representing the Gaussian process that would fit the same points, but just changing this length scale. And by changing the length scale, we start with very small kind of correlation between the points. So any information we got by having those observations is not really translated or doesn't really affect the potential functions that we can get. Whereas once you go to a slightly higher length scale, so that kind of increases the correlation between the different points, and we get a better, at least, well, here, visually better fit, and we're also restricting the space of functions that the Gaussian process would take. And then...
So these hyperparameters are controlling some bias variance trade-off.
Yes, so it's those are things that you can control to a certain extent. And they bias, they kind of bias your Gaussian process and how much it can fit things. You would normally fit those or get those depending on how good, according to a certain metric that we're going to go through in a second. So you kind of try and maximize the marginal likelihood in order to get those functions. So basically, I'm going to go through that. Sorry. So this is just an example. You can use, so...
Can I ask, you had that matrix you want to invert on a previous slide, so... when that is not invertible, like when it's singular.
I think it's the kernels are defined in a way that it's not. It's going to be invertible. That's my understanding, unless someone.
It must depend on the data. If I had some like collinear data in some sense that my space is larger than the.
Yeah, but what I mean is that the kernels are defined in a way that that function would be invertible. So you kind of.
I see at least that like sigma f there. It is like with the multiplying the diagonal.
Yeah, that sigma f would be kind of your error on your function, on your observation. So that's just, yeah.
That comes.
So that's something you can control or you can get from experiments.
Okay, I see. Yeah, because okay, fine. Because it could be some, I don't know, it sort of looks like some regularization parameter almost, so, or like hyperparameter here, but.
Yeah. No, it's not. It's not really a hyperparameter. It's more like the error you have from your experiment. So you kind of you assume that any observations is a distribution, and it has a certain error and the mean. So that error could be very small if you're quite certain with your value, and that might affect things in a certain way. So that's one thing I didn't mention is that you can include in these. Where is it? Sorry. So yeah, you can include in this, instead of just having, like, can you include on top of this like a certain error in this, that kind of smears out the possible functions that can go through that. So in terms of how you can bias your model, so one thing is, the choice of the hyperparameters for the kernel, but you can also choose the right kernel. So the kernel is one way for you to kind of tell tell the algorithm, or like the Gaussian process. That's how I think the real world is. So, for example, you can combine two different kernels. So if we just use, in this case, the Gaussian like the RBF kernel, then you're gonna struggle a little bit to fit something that is linear. But if you tell the Gaussian process from the beginning that use like an RBF kernel plus a linear kernel, that tells you that if 2 points are different, then on top like the covariance could also change linearly, then you might be able to fit your function better. So the choice of kernel is kind of is quite important, and it's one way where you can put in some expert knowledge into your algorithm and make sure that that's kind of reflected on it. And the other thing that I would say at the beginning, when I've been presented with what the Gaussian process is, and the fact that you would say, oh, it gives you the mean and as well as the error or the variance on your data, on your the prediction. It's also quite biased. Like the variance that it gives you would depend on the kernel that you use and the hyperparameter that you use. So it's not as if it's actually telling you this is the final, like this is the real variance that it should have. For example, here you can see that it's giving you quite high variance in this region, and that's mainly because your kernel is biased to think about it in that way. So definitely something to keep in mind. So in order to choose the right kernel or fit the hyperparameters, what we need to do, we need to fit these Gaussian processes. We need to kind of choose the right parameters that best reproduce our data, and for that, what we can use is a maximum marginal likelihood. And in the marginal likelihood, we have two terms. One that tells you about how good your model fits your initial data, as well as you have like a complexity penalty in terms of how complex the model is, or how limited the variance will be. So. And that by using this to kind of, so you can use, so that if you were to use this in any, like if you using like Gaussian process for any tool like scikit-learn to fit your data, then what it will try to do is really maximize your marginal likelihood by going through these, like the hyperparameters of your model, and hopefully find the best ones that reproduce your data. So yeah, and here, yeah, I'm showing a slightly different function where we have some very narrow Gaussians on top of the sinusoid, and here you can see that it's struggling actually to see those. So if we were to use this approach to actually find like a needle in a haystack problem, then it will not really work very well, and we might need to think about it in a slightly different approach. You can also use like a fully Bayesian approach to estimate these hyperparameters, and since we're like, you can use like Monte Carlo MCMC approaches to kind of explore the chemical space and find distributions for these hyperparameters that best fit your model using actual distributions, and that might be a bit more time consuming depending on how your MCMC sampler works. It might be more time consuming, but gives you a little bit more information about how important some hyperparameters are, and if you've defined your kernel in a specific way and you're interested in those hyperparameters, that might be one approach to consider. Okay, so that's me going to all of things related to Gaussian processes. First, before going to the Menti slide, do you have any questions?
I just want to know, is there any sort of criteria of choosing the kernel function? So sometimes people say it's a try and error, the same understanding.
So it's like the choice of kernel depends on, like, as I said, it's one way for you to input like your knowledge about the problem. So you need to really consider what function, like how the function might look like, and then how to use it. It's slightly easier when you have like a smaller dimensions, but when you go to like higher dimensions, it becomes very complicated. And the go-to one, like the one that people start with, it would be like the RBF or kernels. It's not. Yeah, there's. I would say it's not really just a trial and error. There's a lot of thinking that needs to be put into choosing the right kernel if you want to go just stray away from the traditional ones.
It's like, for instance, you want to use the RBF kernel, but you don't know if you combine 2, 3, 4. It's like I can use just one RBF kernel and it's going to fit my data, or combine different RBF kernel, maybe add 2, 3 different hyperparameters.
I think for the RBF kernels, if you were to add them up, it wouldn't really change much. Might be saying nonsense here, but just my understanding is that it shouldn't. It wouldn't affect it. Might make it slightly harder to do to fit or to find the right hyperparameters. Yeah, the approach that I've used so far is really just to start with the RBF kernel and see how it works, and then think about the problem and see if you need to have some to add more complexity into your kernel.
At least you can. If you have like several kernels, then you can change the tails, for example.
So yeah. So I think for the example I was showing there is like, if you know that you should have some kind of linear aspect and you only have observations before a certain time, let's say you're trying to fit some temporal data and you've got information up until a certain time, but you also know that there is a kind of linear increase embedded into your data, then you can include that into your kernel so that it actually predicts things that are out of your observations pretty well. But again, that's it's if you know that, you can put it, but otherwise.
In materials design, we often know a subset of functions that we wish to use. So we don't. The multivariate Gaussians seem quite general. perhaps arbitrary, but there's no limit on the sets of surrogate functions we can use? Does the machinery change if you choose to use different surrogate functions?
So going from Gaussian processes to something else. So I think the machinery here so far has been described for I've described it for Gaussian processes, and it relies a lot on the use of Gaussians for the whole derivation. And so if you want to use a different surrogate function, what you need to make sure of is that you have a mean and the variance that comes out of your surrogate function. And to get that, you can use any other function. So it's not the use of Bayesian optimization is not limited to using Gaussian processes. But in order to get the variance, the Gaussian processes are quite a versatile tool for doing that. But yeah, I would say I haven't really looked into it in more detail. I know that you can, for example, use decision trees or for doing the prediction and using ensemble models to get the variance. But that's a whole different kind of machinery from what I've presented.
I wonder, have you seen other point processes being used, let's say, I don't know, like Poisson or I don't know, Dirichlet, or if you just replace the Gaussian process with some other process, so that would be better for some, I don't know, more discrete data, which is, you sort of have a big discrete process.
I haven't seen that, but yeah, it's so far in the literature what I've seen is really mainly using Gaussian processes, and even using other methods are not very common. But I think there might be a side of the literature that I haven't explored yet. But you're more than welcome to try to look into that in your posters as well. Going back to the side, do you have any more questions? I think
for the application side, I don't know, maybe the limitation for maybe the size of your training data, because you need to compute the covariance matrix for, you have maybe 1 million or 1 billion data set. Can you still use the Gaussian process?
So I would say Gaussian processes are mainly you would refrain from using them when you have millions of data points, and the approach to kind of overcome that would be to do some subsampling. That's kind of the main approach to use Gaussian processes on large number of data. So you kind of do subsampling just to get the points that are the most interesting in your data set, or the most representative in your data set, and use that into your Gaussian process. There is another way of where you can try and be slightly clever on the way you invert your matrix, and that those are approaches we can use some kind of approximate method to get the inverse of the matrix and speed up the calculation. And it's a whole field of work on using Gaussian processes for larger data set. But yeah, that's kind of my take on it. If anyone has got any other, we've got experts on the field, so if they want to.
So the way to limit overfitting in your example, the Gaussian process would be to increase the penalty factor for the complexity of the kernel, right? How would you control for overfitting in the Gaussian process?
Yes. So yeah, you would.
That's kind of the equivalent of a regularization.
Yeah, so if you want to kind of avoid overfitting, you can try and play around with that kind of the complexity penalty. So you might want to kind of increase the importance of the complexity penalty. Don't know exactly. I haven't really tweaked that formula a lot, but you could potentially focus on marginal likelihood that has slightly tweaked kind of complexity and reduce the bias in your data. But then I don't know how you can affect the bias. There's a difference between the bias coming from the kernel and the bias coming from the hyperparameters, and those two can it's very hard to actually find the right one, and how to assess that. But that's something to keep in mind. Okay, so just at this point, we could I don't know if people want to have a small break for 5-10 minutes just to get some water or something, or shall we just carry on? It's up to you. We can just carry on. We've got like, I think we're at almost the hour mark. We've been through what I would consider the most mathematical bit of the talk, so
Sorry, guys.
it's all right.
I need like leg support.
Do you want some water or something?
Good, I'm good. I just wanted leg support.
Yes. Okay, so here, so we've got another slide on Menti, and this is more like of an open question. And it's, so far, we've been discussing like these Gaussian processes, so I should have had this question before we had the whole discussion, but again, can you just tell me like what are the limitations of Gaussian processes for regression, and how do you think it's going to affect using those for like material discovery aspects? It's, yeah, so here, feel free to say whatever you want. It will be also interesting for me to have the responses. Online, do you also have some questions or anything? I'm sorry, I didn't really interact too much with you online, but if you have any questions, just shout.
Yeah, sure. No, everything is fine so far.
Okay, cool. Okay, so we've got a lot of answers, and we can kind of group them to a certain extent around problems related to the scale and how the Gaussian process would scale with the number of training data. Then there is the sensitivity to outliers and the choice of optimal kernel and hyperparameter might be too costly. That's interesting. There's lack of knowledge of underlying function. Okay, yeah. Might have added like another question on this, and what would be an alternative? Or can you think of an alternative? If anyone has an answer on that, that would be great. If not, don't have to.
Use neural network.
Okay. And would that kind of overcome the problems we're... The neural network would be great, like for addressing the problem with training data, but is that going to be better, for example, for defining outliers, or how overcoming the bias of your predictive model? I'm not singling you out, but it's definitely an interesting alternative, and people are looking into that. Good.
So another tangential question. So what's the interpretability of Gaussian process? Like if I use supervised learning, say tree-based method or like a linear something model, then those weights kind of tell me which features like help in the prediction. But here, like, what is my source for interpretability?
Does anyone have an answer?
Could you repeat the question with the buzzing? I couldn't.
No, like how interpretable are Gaussian processes? Like if I compare to a linear model or a tree-based method, right? Then I have some notion of interpretability. Like the weights tell me how much each feature contributes to the prediction. Whereas here, there's a process. You're drawing from a distribution. What can I say about like how much like if a material is represented using different I don't even know, elasticity or like something plasticity, I'm coming up with features, but how do you know which one is contributing to your acquisition function or something, like the performance measure?
The interpretation is probably high level, so it's like goes under the stochastic processes and functional approximation, so it's not like really not very easy.
Well, one thing you can look into is the hyperparameters you use for your kernel, and that kind of the like for example in RBF kernel, the distance hyperparameter could tell you how strong one what made the Gaussian process decide on certain mean for that specific point. You could kind of take an approach where you take off some data from your data set and see how it performs and how much it changes, potentially pinpoint whether like the prediction, like what the prediction of the Gaussian process is related to, which point is it related to, or which property of the material it's related to. I think it might be slightly more complex or like more demanding than just doing it with like decision tree where it's clear and you can get that out. But you could, in practice, do it by kind of looking at the dimensions, like the length dimension for like the length parameter for each. If you have length parameter for different dimensions, then you can look into that. You can do some kind of take out some data from your data set and look into how they change. But yeah, it's not as simple to interpret, but it might be potentially like a bit more easier to look into the interpretability issue than neural networks, where things are slightly more like random to a certain extent. I don't know. That's my point of view.
In the end, you still have a set of weights, right? Like how it arrived at the weights is not interpretable, but I think like even in the end, like you still have like a set of weights that you can do some inference on.
But those weights are also random.
I have here also a well-defined model. It's very different than neural network.
Yeah.
Yeah, under some limit, there actually might be equal. Like if you take some like n to infinity limit with some dimensions of the neural network, you might be able to show that the Gaussian process and the neural network are actually the same thing. But you can do the same thing as with any black box. Try to do these like Shapley values or any other like techniques how to make sense of the black box model. Of this GP surrogate you fit in during this Bayesian optimization, which is like the loop around the.
Yeah, and also the question of the interpretability might be important for the prediction, but if you're just using it in kind of closed loop optimization approach, as long as it works, it might be all right. That's kind of another take on it. That's one way you can think about it. I don't really need to understand how it got to the end result. If you manage to get it within the constraint, it doesn't like start making some product that can be very harmful or dangerous or it can explode. But as long as it respects certain constraint and it optimizes it, then that's all right. But yeah, things to consider for my next lecture. Okay, so thanks a lot for this. Do we have any other comment on these points, or shall we move on? Okay, so in my case, like so in terms of limitations, the things I've picked up would be like the slow inference, how it kind of scales badly with the size of your observed data. The importance of choosing a covariance kernel, or like your kernel, and how can you take out bias from choosing that kernel, or how to choose the right kernel for the right application. There's also the question that Gaussian processes are in some sense idealization, and that you could have like a different approach than Gaussian that are more suitable for your application, and that comes back to what Ben mentioned. And then there is loss of efficiency in high-dimensional space. So if Gaussian processes are quite efficient when the space is around like 10 to 100 different variables, but then it doesn't really do very well, and that's mainly because in high-dimensional spaces the distances are very hard to compute, are very hard to interpret, and might not have any meaning anymore because it's another question. Okay, so going back to knowing what Gaussian process is, so here we're using that for Bayesian optimization. So we're basically what we're trying to do is use this kind of surrogate, like Gaussian process as a surrogate function, and that gives us the mean and the variance of the predictive function, like the surrogate function, and based on that we would need to optimize the acquisition function. And that's kind of the question of how are you going to choose the next point to evaluate. Let's say we've got these 5 different observations. We've managed to fit it with this Gaussian process. Now, what do we do with it? Where to evaluate next? And to decide on where to evaluate next, that's where we're going to look into optimizing the acquisition function. There's different types of acquisition function that we can use, and they span from simple ones, that is like lower or upper confidence bound, that is like you just take your function as linear combination of your mean and the variance on each point with a certain factor that defines your exploration. Yes?
So I have a problem with the mean function. It seems that people are not paying attention to the mean function for Gaussian process.
What do you mean by the mean function?
Function, you problem statement, you assume that your f is a GP with a mean mu f of x sigma f. So people are paying more attention on the covariance function. Why? Lots of people, they put the mean equal to 0 and not a specific function.
So my understanding of your question or your observation would be that people, what you would, the input data that you put in, you would normalize it so that your mean is at 0 and you just have your variance. But then the mean that is predicted for your Gaussian process, that's quite important, and that kind of defines the value, that has the value of your Gaussian process at a certain point. So the mean here is kind of something that you calculate, and you calculate it using the formulas I showed before. But the input, you want it to be kind of normalized. You want to so that it's easier, and also it makes a bit more sense. So the first step whenever you're using like these Gaussian processes is that you need to kind of normalize your input and output. You normalize it according to your observations, which might affect the space that you're looking at. But that's kind of my understanding of the question. I don't know if that's different from what you've came across.
I didn't pose my question. Well, I mean, in the prior distribution, put your prior distribution as a Gaussian distribution of mean 0 and a certain covariance function. Compute your posterior distribution after observing the data. So the question is why people always, I don't know if it's always, they put the prior distribution, they put the mean equal to 0.
Are you talking about this? So like the starting point. So in the starting point, these are like all the possible functions in this space, and you kind of describe it as a prior with a mean of 0 and and certain variance, and that variance, your prior should not be very restrictive on and should not have a major impact. I didn't really go through that a lot in here, because ideally what you don't want to restrict your posterior distribution by your prior a lot, unless you have some clear understanding of your space. But ideally, you start with some like distribution of function or with a mean of 0, and then as soon as you have some observations, you compute your new mean, and that gives you this new like red dot line, for example. Is that clear?
Implicit assumption that like your function values will be somewhat close to, well, not close, but close to 0. Like if for some reason you know your function can only take values between like 10 and 11, maybe you'll put your prior at like 10.5.
Yeah, but so that's kind of that's where you do your pre-processing before on your data to normalize it, so that this you can start from the same point.
Yeah.
So that's kind of why the normalization is important. But then it doesn't really matter too much. You could either normalize it at the beginning or take the mean of your observed data as your new as your prior for your prior distribution. But again, that's I'm just thinking about it from an application point of view and just simplifying the maths to a certain extent. That's my understanding. But I hope that was clear enough. But happy to talk about it more later if you want. So I was talking about the different acquisition functions. So you could either have simple kind of analytic ones, or you could have an expected improvement. That's one that is often used, where you try and you look at expected improvement of your initial function depending on your mean and variance over the best that has been observed so far. And you can calculate that, and it gives you so basically you look to compute your acquisition function on your space, and then you take the maximum of your acquisition function or your minimum depending on how you defined it, and you would evaluate your function on that point again. Hence, when you're doing this Bayesian optimization, so there's a requirement for you to actually optimize this acquisition function, or evaluate it on the space and do the optimization of the acquisition function in some way. And you can do it normally, your acquisition function should be something that is easier to compute, and you can compute it quite fast. Hence, if you have a Gaussian process with a lot of observed data, that might be a problem, and you start competing with how slow you can compute your acquisition function as well as compared to your the main function that you want to optimize. So if you're working on continuous space, you can optimize your acquisition function using any numerical optimization method, because these are very well behaved functions. When looking into discrete or mixed variable space, which is quite common in materials, that becomes slightly more complex, and that's something that you need to keep in mind on how are you going to be able to optimize your function. If you have your space is the possible kind of molecules that are out there, how are you going to be able to optimize your acquisition function over that space? And that's something we can we're going to talk about later as a major thing in for Bayesian optimization for material discovery. So again, I'm just coming back to this the initial problem statement, where what we're trying to do, for example, here is really find the right molecules to use for this application and explore this space that is here. It can be a mixture between the type of molecule that you're using and the way you're gonna make the film. For example, the how much the concentration of your material on your that you're going to use in the solution, or the temperature that you're going to use for the deposition. So those could be kind of continuous variables, as well as discrete variables. So the problem when you're thinking about material, like using this Bayesian optimization for material discovery, you really need to think about this mixed space problem and how can you optimize or how can you use it in this space. Yes, got a Menti again. And here my question is, what are the challenges of using Bayesian optimization for material discovery? So I've covered a few of them, but I would like to have your take on this.
So these are challenges specific to material discovery, not some of the challenges we've already.
Well, if they apply as well to material discovery, you can put them in. It's in general what are the challenges of using the Bayesian optimization for material discovery. So if the problem is that we have too much data and the Gaussian process is not good, then that might be also something to consider. Although I don't think that's the case. It's more like, depending on the problem, it's more of a small data problem. Interpret it a bit.
I didn't go back.
We cannot always measure the activity descriptors and would give us insight. Bio, in this case, would not lead to new understanding. That's quite interesting. If your data does not represent all aspects of the parameter space, you might miss out on promising materials. Can it support? That's more of a question than a challenge, but but that's just on the question of can it support explore and exploit in reinforcement learning sense, you can enforce it through using the right acquisition function. So instead of, for example, in the upper confidence bound acquisition function, you can increase how much importance you put into the variance as compared to the mean. And that way you would force the algorithm to go search in places that it doesn't know much. So that's definitely something you can control in that way. And you can even have, within your Bayesian optimization approach, you start with a different acquisition function to learn as much from your space as possible, and then use a more exploitative acquisition function that guides you towards the minimum. So if you don't want to you don't want to face the problem of finding just a local minimum, for example. But optimization is hard. Okay, how does that relate to Bayesian optimization in general? Is it any optimization approach is hard, or optimization in the material space is not something we should be considering? Noisy measurement, cost of querying the material space, non-smooth objective functions. Yes. So I think, all of these are problems that are quite relevant for material discovery. the nature of your objective function. So if your objective function is not very smooth, as we've seen in the example before, then your Bayesian optimization might not actually work, might not give you the minima, and might just struggle a lot. It might, depending on your kernel, you might have smoothened it too much for it to be relevant for the type of problems that we're facing for material discovery. And the type of problems that we're facing in material discovery is really looking for specific material that has a certain number of property, and that material can be quite unique within the space. Like depending on how you define your space, it might be kind of needle in a haystack problem. Cost of querying the material space, so that's definitely something to consider. So you can overcome that through using like computational approaches instead of doing like fully experimental. But then the problem is the computational approaches are not always very accurate, and they're also just an approximation of the real world. And sometimes, even if you using computational approaches have not been the most efficient methods in material discovery. It can kind of speed up things, and we, from a computational chemist point of view, we think that it should have an impact, but it struggles in real life. So, and also there's the question of, you can have a very complex model, but sometimes even a complex model is not very good to explain the experiment, and you might spend too much time running some calculations that don't really relate to the real life in any way. Okay, I might move on, but does anyone want to comment on these in any way? I've been mumbling on my side, but.
So, a question, with this non-smooth objective function, okay, you might miss a sharp peak, but probably it will still help you to find a better set of materials, which, depending on the setting, might be fine, because there might be some weird combination of molecules that gives a super good property, but you might also just miss out on this peak and find a smoother peak where it has some nice properties as well, and that's okay, and that's good.
Yes, yeah, definitely. So that's kind of that would be one way of looking at it, is that at least using these approaches, even if you're missing the very best one, you're kind of guiding towards things that are really good. But then one thing to consider is, what is the alternative? So the alternative of what people are using nowadays is really taking a specific material that is working very well, looking at a very, very small, narrow space and doing experiments on that. And then they manage to improve quite a lot. So using Bayesian optimization, or you want to kind of explore a bit more, but then you might kind of not be as efficient as if someone just focuses. But you could use also Bayesian optimization to help you on that very specific question. That might also be another thing. Again, it's different approaches. I'm gonna move on, and now we're gonna go slightly more into what's material discovery and what are the problems. So far we haven't really, there was some question about graph kernels. There was some comment on graph kernels. I don't know where it's coming from, but we haven't really talked about the representations, or what are the other problems when looking at materials. So we know that materials, or molecules, are these entities that we found that we can describe in some way, but they're not continuous numbers. It's very hard. It's not a space that is easy to describe mathematically, and we can use different approaches to describe them from a mathematics point of view, or as mathematical objects. That's one of the main challenges for using like Bayesian optimization or like any optimization approach for material discovery is how do you actually describe these objects from a mathematical point of view, and what is the function that you're going to use to that you're trying to kind of minimize or maximize using your Bayesian optimization process. And here is like few examples of things that you can look into or that you want to kind of optimize. For example, let's say want to optimize a certain reaction in terms of giving you the highest yield of this reaction, how like the highest number of successful chemical the highest successful kind of chemical reactions that happen, and you want to optimize for that through changing how you do your chemistry and like at which pressure, which temperature, what solvent you use, what other additives. So additives would be like some small molecules that you add in. Solvents would depend on would also be described as molecules, or you can describe them as having a certain number of properties. And to go from, so let's say you want to optimize for this type of reaction, so you need to define your reaction like in a certain way, and you can define it as certain, like as a string with like adding element 1 plus element 2 gives you element 3, and this kind of string description, you could use that to define certain function on it, or you could use some fingerprints that is like, if you think about these as graphs, so a fingerprint would give you the similar, like let's say the similar elements that would be found in for each for all the elements you have in your space, and you can define that as 0 or 1, whether you have that kind of substructure in your graph or not, and that gives you your fingerprint representation, and that would be like a discrete representation with a certain dimension. There are other ways of you can also use directly graph representations on your molecule, or your protein. You can use like some sequenced strings or structural graphs, and so the choice of this representation is quite important. And these kind of mathematical objects makes the complexity of using the Gaussian processes for material discovery, and hence you need to kind of define those at the beginning, and then think about what would be a kernel. How would you define a kernel for each one of these mathematical objects, for example? If we take molecular graphs, you can think about how would you define the distance between the two graphs, and that's like a question that needs to be looked into, or like the difference between strings and things like that. You can use like nowadays natural language also would be quite helpful, especially when working with strings. So that could be that's another area of research where people are using like natural languages for this type of applications. And then in terms of how do you use Bayesian optimization for material discovery, so you can either use it to accelerate kind of in an automated experiment approach, where let's say you have like self-driving lab, you have a robot that is doing certain number of that has certain number of possible things he can do to make the material that you want, like choose amongst the different temperatures, choose amongst the different solvents or things like that, and then you use Bayesian optimization to guide you towards like choosing the right combination of operations, or to get the best material out of it. There are a few examples in the literature on that. There's quite a lot of work on discovering and using it like in actual experimental approach. There's also a lot of work on accelerating computational discovery, so how to use, and so the difference between these two, I would say, is that one would be mainly focused on using Bayesian optimization on like continuous space, whereas the computational approach are mainly like looking into this problem of representation and how to improve the representation for a specific Bayesian optimization. And it has not been used, like it has started, like the use of Bayesian optimization has started quite recently, like in the last 5 years in the field, and it has a lot of potential, but so far it has not been yet used to discover something extremely new. And most of the applications, they either like find something that is as good as the materials in out there, or they're just used on like some kind of simplified problem, or like not like the simple data sets, just to showcase that Bayesian optimization is actually useful for computational discovery. But in terms of experiment, like actual impact of Bayesian optimization, I haven't found anything on that, and you're all welcome to try and, if you want to look into it in your posters, to try and find something in literature that actually showcase the use of Bayesian optimization for that. And then, yeah, so I want to just briefly introduce, we've got 25 minutes left. I'm just going to briefly go through some papers talking about like benchmarking Bayesian optimization in this for material discovery, just to show you kind of have a flavor of what's out there in literature. So here, for this example, they looked at different problems, different data sets, and that have different sizes, and they look at different type of material, and each material can be described with different dimensions. So these are applications for like real experiment, hence it's more like Bayesian optimization in the continuous space. And what so they look into these different data set, and here we're just looking at the distributions of the material and what we're looking for, so just to see how hard like the optimization problem might be. Then they looked into benchmarking this Bayesian optimization, so how good different approaches would be. And whenever we're talking about benchmark, we need to consider what's the performance metric that we're looking at. And the performance metrics that they talked about here in this paper would be finding a certain number of the top candidates amongst the number of total top candidates. So after a certain number of evaluation, how many of the best ones have you found out of the total ones? And then there's the enhancement factor, that is how much you've improved compared to the random. And then there is another one that is just I forgot the name of that, and I didn't put it in here. But basically that gives you the number of the top ones compared to random, like divided by the random. It's the learning cycle to find top ones amongst A. So that would be kind of here looking at either this line compared to the random, or that the horizontal line compared to random. And in this example, they looked at either using Gaussian processes with different kernels. They mainly looked at the Maton kernel with different acquisition functions, and they also compared it to a random forest approach, where instead of using Gaussian process, you just use a random forest to give you the mean and the variance of your data. And here they showed that on most of the problems that they looked at, well, Gaussian process is an improvement over random, which is not surprising, but it's still underperforms over compared to the random forest. And these red ones are like Gaussian processes with slightly more advanced kernels that has like a learning rate, like a length scale for each variable, and those perform as good or slightly better than random forest. So in this is it's been published in 2021, and here the way they benchmark it is really just taking a lot of problems and trying different methods without actually trying to think about how to adapt the kernels, for example, to the specific problems and things like that. So I wanted to just show this paper as a way to think about, well, how do we actually benchmark, and what would be a way to benchmark like Bayesian optimization approaches for material discovery. Do you have any thought on that? So another way of saying it is, okay, we've got this very nice algorithm. We know that there's a lot of things we need to tweak for it to work. And then if we were to kind of showcase that our new method or new algorithm or slightly different approach works better, how would we be able to show that on, like, how would we do it in a consistent way? Okay, so that's all right. I might, need to kind of reconsider this part. But the benchmarking, I thought about it as quite important, and thinking about how you compare different approaches, and when, like, for example, if you're doing research on this field, how would you be able to showcase that your approach is better than someone else's? So far, it's very hard to benchmark for Bayesian optimization, especially that, as we've seen, like, the problems are quite, like, the methods sometimes are very problem specific. It's very hard to say that, this specific approach is better, or we've got X enhancement over a normal method. We can compare it, like, for example, to the random, that's fine. But the other methods might be slightly, comparing to other methods might be slightly more demanding or different, and the question might be ill posed in that way. Rather than thinking about comparing different methods, you just see how good your approach is, and then how it worked on that. Like, if it works for your specific problem, then it's fine. You can always just show that.
How about, like, because you haven't, let's say, discussed much about the underlying, like, computational model you're using. It might be arbitrary almost, in principle, right? So, can you in practice, let's say, assume that you have some solid state discovery problem, and you have a bunch of known materials. Are people able to discover these known materials using that simulation and then some GPPO or whatever optimization method? So, are you able to discover known materials using the simulator and these methods?
Well, the answer would be yes. But then the problem is that if you were to benchmark on that...
How well? Because if definitely, I mean, assuming the simulator works really okay and it's tuned against known material data, then yes. But then, like, if you didn't know all the parameters, and you didn't tune against, like, experimental data, the simulator, like, because it probably has some internal pre-parameters which you need to, which are fixed in this process. You sort of, like, calibrate it, and you trust that it is actually a useful simulator.
Yeah, so that kind of goes back to my answer. I would say yes, because you can put in any prior knowledge into your model and make it work for that specific purpose. So if you already know the data set you're targeting, then you can kind of tweak it to work for that data set very well. It's very hard to assess how good it will do on an unknown space. And that's kind of the same problem you would face with any other, like, machine learning approach, where you're trying to assess how good your model is.
I just wonder how ab initio these methods actually are, like these simulators, these computational, let's say, material physics or material chemistry. Like, are they actually more like a parameterizations of already existing data, or can they actually, like, model enough, like, first principles?
Okay, so that's...
Discovery is, like, feasible at all, like, so that's the basic question.
That brings us, back to the question of evaluation and computational methods for evaluating a certain material. So ideally what you want to do is, let's say you have a certain material, like a certain molecule, so you know its chemical structure. So the properties that you're trying to evaluate relates to the electronic wave function and the atomic positions. And to get the properties, which would be like, let's say, for example, looking at properties related to light absorption, these are properties that you need to get, that you can get from solving the Schrödinger equation. I'm straying a bit far going back to physics, but solving this kind of many-body Schrödinger equation it would give you these properties. The problem is you cannot calculate that for a large system. You can calculate it for like hydrogen or like hydrogen atom, but you cannot calculate it for larger molecules. And for that, we use like some approximated methods, such as, for example, density functional theory, and those are have got some kind of parameterization that goes into them. And that parameterization would definitely affect your discovery problem. And that can be one of the main issues that we're facing nowadays with actually having an efficient material discovery approach that is mainly based on computational. It's because the things that we're trying to discover are out of distribution compared to the things that we already know, and everything that like the models that we've developed are only based on what you know. So, that's definitely a problem that unless you can actually solve it perfectly, then you will always have that issue. But you can have some kind of approximation, kind of try and use some, like within the Bayesian optimization approach, you can mix both an experimental and a computational approach using like some kind of multi-fidelity approach, where you use like your low fidelity computational method as well as like a high fidelity experimental method to learn how much to learn the error between your theory and your experiment, and then guide your discovery in that sense. So that's one of the other things that I haven't mentioned a lot, but you can kind of incorporate that into your discovery approach, and you can have that kind of uncertainty between experiment and theory incorporated in your material discovery approach. Always stray far, but I hope that was all right. I might need to start going to the other bit, but this is just another benchmarking paper if you want to have a look at it. And here they were looking at like more recent methods using different descriptions and things like that, and they showed that depending on the application, some of them work better than others, and it's very hard to do the benchmarking. Okay, so the last bit is very much related to my own work, and this is the work that I've been doing during the past few months, looking at how can you use Bayesian optimization to discover some materials within a certain space. So the problem that I'm looking into is, okay, I've got my search space is defined as these type of molecules. So molecules that are that can be built from fragments. So each one of these fragments can be defined within a database. Then you can define a certain way how you can connect these different fragments, and then you define your search space in that way. So, for example, here, if we just take 140 different fragments, you can connect them in 300. Like you get 330 different elements, meaning 330 different unique fragments plus connection rule. And then that gives you up more than 10 to the power of 13 different oligomers that you can look into. You can restrict your space by defining some kind of symmetry rules where some fragments need to be similar, or some fragments need to obey a certain number of rules, or would need to have a certain specific property that you already know from the fragment database that you have. So that's kind of the problem we're looking into, and how to explore this space. So it looks like kind of combinatorial problem. But it's also kind of exploring in a very discrete space. So how do we do, what is the most the best approach to do this. In terms of evaluation method, okay, so in terms of the evaluation method, what you do is that I'm using. So first you build your molecule, then you need to do some quantum chemical calculation that I was talking about just before, so trying to solve this Schrödinger equation with some approximate method. You need to generate an initial geometry. So you start with an initial geometry, and then you need to solve to find the right geometry that this molecule would have in nature, because you cannot just define, because the properties of the molecule would be related to this geometry that it actually takes in space, because solving the Schrödinger equation, you can only solve it with frozen atoms, but you need to find the right geometry that minimizes the energy. And then from that, you calculate your properties. So basically, just to show you how the different steps for you to get from input to output, and how, there's no clear correlation between which fragment you use at the beginning and the property that you get. Because even if you just change one fragment within the molecule, it can change or alter its geometry a lot, and that would give you a very different property at the end. Also the kind of predicting that geometry is quite hard, and this step takes quite a chunk of time, so you don't want to do that. So the search algorithms I've looked into is one is just heuristic approaches, evolution algorithm or random search, and two model-based approaches. One is Bayesian optimization, and using a surrogate model inside of your evolution algorithm. I'm going to go through those in slightly more detail here. So what is an evolution algorithm? So you start with your initial space. You take a certain number of parents. So it's very much like what you have in nature. You start with you select a number of parents. You do some mutations or crossovers between the parents, and then you generate a new population, and then you just select one element from you can randomly select one element from this population that is within your search space, and then you evaluate it. So that kind of approach, you're kind of assuming that the property of your molecule is related to you know that the property is related to the fragments, and you're assuming that the parents would having good parents would give you good children, basically, and that approach is quite efficient on its own without having anything else. You can improve it by using some kind of surrogate model. So here you can just use, instead of selecting randomly from your search space, you just use a surrogate model to give you the mean, to predict how good these molecules would be if you evaluated them. So, and then you pick the best one amongst that. So this surrogate model would be trained separately, and you could use a neural network or any other method to do the training, and use that to kind of help you with your search approach. Then the Bayesian optimization, that's what we've been talking about, and in this case, so it's the same thing as we've been looking into. The only thing that I've looked into here for the Bayesian optimization is two different types of representations. So in order to represent my molecule, you either represent it with an array of the properties of each of the fragments, or the fingerprint representing each of these fragments. So you just take an array of dimension n that defines your fragment, and then concatenate that, and that would be your representation, and that's where you're doing your Bayesian optimization on. Or you can learn this representation through using let's say, in this case, I'm going to talk about graph neural network to go from your inputs to a certain representation for your output that is well correlated with the value that you're trying to predict. And then in terms of the acquisition function and how I optimized it, in my case, I used an evolution algorithm to optimize the acquisition function in this space. So here, it's kind of using the same approach I described for the whole thing, but you can just use it to optimize the acquisition function in the loop whilst you're doing the active the search every time. And you can define how you the convergence criteria depending on how time consuming the calculation of the acquisition function is, and what you want to get out of it.
That's right. So when you have this, at the end you suggest the element, and then you loop back into the search space. At that point, you also need to evaluate?
Yeah.
Okay. And then would you use like the surrogate model you used in the evolutionary algorithm? No, you would test it.
Yeah, so here it's like the evaluation is always the same, like the big evaluation or like the function the black box function that we're trying to maximize is that evaluation I've talked about. So the surrogate model is only there to help you. It's trained on the data that you've gathered so far. Yes.
Okay, and so because in the evolutionary algorithm, you're gonna have a lot of evaluation, so it's not feasible to do the long evaluations every time.
Well, here, so it's the same. Like the step of suggesting a new element is the one I've described here. So once you've suggested a new element, that's the one you're gonna evaluate.
With the long evaluation.
Yes.
Okay. So
so you don't have to evaluate all the elements in your population.
So in this 10,000 population, you use the surrogate model to select one within the 10,000.
Exactly.
And then you send it back.
Exactly. Or you just select randomly if you just want to use a model-free approach. Might need to go quickly. This is just me showing the data sets that are the different properties that we're going to be talking about. I might just focus quickly on these two here. So this is we're trying to maximize for the target value for this ionization potential or IP around 5.5, and there is quite a lot of molecules already there on our data set that are quite close. And for the oscillator strength, we're trying to fit something that is as big, that has a target of 10. And here we have a very, very few elements in that with that value. And so it's there, and then I'm just going to show an example of using Bayesian, the optimization approach to find the molecule that fits in with that target. So if we just use a Bayesian optimization with the property, just concatenating the properties of the fragments, we get quite similar kind of performance between the bio and the evolution algorithm. I'm showing three different kind of evaluation metrics here. So the first one is finding the maximum after a certain number of iterations, the mean value of the element found in that after X evaluation. So here I'm showing the 25 different runs and the mean value. Hence you have certain distribution of those values. And here is just telling you how good the molecules that it suggests are in general. And then here it's finding the top 0.1%, so out of 82,000 molecules, finding one amongst the 82 best molecules that fits that target. So how good your model is. So far here, for the oscillator strength, that's both quite unique, it's very quite a unique property, as well as being quite hard to estimate using just the representation that we're using here. We don't really get any improvement between the Bayesian optimization or the EA as compared to the ionization potential, which is a property that we found slightly more of it, and also it's more correlated with the property, with the representation that we use. So here we have a small improvement over the mean, and we managed to get more of the molecules over time. So it's not basically here, even if you have a good instinct about how these properties would affect the property that you're looking into, it doesn't really give you much improvement, especially on this example data set. So, hence, it's quite important to have the right representation for your molecule, or a representation that is actually related to your data. So I started with these, and I was quite bumped out But then since by running this quite a few times, I've generated all these data set. So I was like, why not use that data set? And is there a way to actually use the information I've got from that data set into my Bayesian optimization rather than having a representation that I've set from the beginning? Can I do something a bit better? And that's where I came out, like when I started working on this, where we could use it, you could call it like deep kernel approach, where you're trying to learn the representation using like deep learning. So the idea here is we use, like if we have the geometry or the XYZ of the molecule in the data set, so we could use like a graph neural network to predict, to train, like we train a graph neural network to predict one of the target tasks that we're looking into. And we can use, so the way the GNN would work is it would give you like first embedding, like an embedding in certain dimension for your molecule representation, and then you use like just a linear, just a simple feed-forward neural network to predict the target. And then basically what you want to try and get, or like what you would use as an input for the Gaussian process would be this kind of embedding. This new representation. The problem is we don't have that XYZ representation for the molecules that we have not calculated yet. So we need to learn that embedding from inputs from the fragment. I'm not going to go into too much detail of that, but you can just start from input fragments and get to the embedding. So you can learn this, and then you can use this embedding for your Bayesian, for your Gaussian process, or for your EA surrogate model. So your EA surrogate model would be using this kind of feed-forward neural network that you've trained before. This is just how the model training works and how it changes with the number of molecules, but I'm not going to go to that because there's not much time. Am I allowed to go over time? Okay. So this is, again, just the performance, but I wanted just to finish up with saying, yeah, so once you learn, like you use the learned representation, you get quite a big improvement over the evolution algorithm in terms of how good the model works, like the search algorithm works. So if we just look at the green one, the learned bio is much better than the EA. It's, or like the surrogate model gives you more points you towards, like, or suggests more elements that have in average a higher mean value, but it's very hard to find good ones. So it performs worse than an EA on its own to find the best ones that are out of the distribution. So I didn't mention it, but the best 1,000 molecules are not included in the training and validation set. So the model does not have any information about those. Hence, the surrogate model is quite biased and is not it doesn't perform very well in there, and it doesn't predict ones that are good. That's mainly for the oscillator strength, whereas for the IP, we have a better, like the surrogate model works better because this property is easier to predict to a certain extent. And that's, this is just on the number of molecules. I didn't spend too much time on this, but this is just kind of giving you an overview or a taste of what I've been doing and what research in this area might look like. So for me, what I would do next is potentially like look at more advanced kernels and how can actually adapt the kernel better for the problem, use potentially like a multi-fidelity approach for this. So I hope that throughout this presentation, and I think it was more of discussion, I've managed to give you a taste of what is Bayesian, how we could use Bayesian optimization to accelerate material discovery. Also, I hope that we've managed to, you understand a bit more how you need, with the problems with material representation and kernel definition for this approach, and how we can optimize acquisition function on a discrete space, and how hard it is to actually use Bayesian optimization for real-world applications. And I would just leave this here in terms of potential subject that you could look into if you are interested in the subject, and ask you if you have any questions on the subject.